Hi, my name is Bimal. Me and my group conducted an experiment comparing thermal properties of chocolate milk and soy milk. To do this, we needed to do an experiment to see how it would react when facing the same surface temperature coming off of a stove. So we placed a stainless steel pan and about 350 milliliters of soy milk into the pan, which was then we put it on top of the stove facing a constant temperature. So we wanted to get an exact reading of how much the surface temperature would be of the soy milk, but it didn't go as planned because it spread up and was all over the place and got a little messy. And we just after that we just assumed, since soy milk is similar to water and water boils at 212 degrees Fahrenheit, but soy milk is a little more viscous and has more density than water, we just assumed its surface temperature to be at 214 degrees Fahrenheit. And then again with chocolate milk, we also had to make an assumption because it was getting dangerous to conduct the same experiment. So the chocolate milk is even more viscous and more dense than the soy milk, so we assumed its surface temperature would be at 216, as I should say. And after that, we recorded those and later analyzed the data to get the heat flux and everything, which will be discussed by my friend Zach. And as you can see, the milk boiling, and that measurement was just for measurement's sake. That has nothing to do with it, but the fluid bulked up and it was causing all sorts of problems, so we had to assume certain things.
As Bimal stated, we had to set up a real-world experiment. Our experiment was a hot cocoa party where a vegan is in attendance. We solved this issue through the use of silk soy milk with additives such as Hershey's hot cocoa powder mix, which is certified vegan. In the industry, nanofluids is the analogous example. Nanofluids are bulk fluids in which the thermal conductivity is originally very low. However, we use bulk fluids for which we know the properties already, and then suspend nanoparticles such as glass particles, which are spheres, and propant, which act as an increased surface area. Within the bulk fluid. And then we analyze how they act throughout the fluid. The equations that we use through experimentation are the continuity, the momentum, and the energy equations, for which certain parameters are held constant. The interesting matter, though, is in the nanoparticle continuity equation, for which the diffusivity is found using the Einstein-Stokes equation, which uses the Boltzmann constant and the viscosity of the fluid to find the diffusivity. These equations, however, are only used in single phase. In industry, though, and in also real life examples, we come across multi-phase examples, especially in the culinary field. For these kinds of examples, we have multi-phase. Multi-phase in heat transfer, though, requires us to deal with gravity as well as Brownian motion and friction.
Hi, my name is Zachary Goulet. You just heard from Avery. She kind of gave more of the real-world application as for what we could do with this experiment. And after Bimal kind of gave you more of an intro into the experiment, I'm going to show you the kind of the implication I went into and the calculation of the backbone of the math and heat properties that you're going to see presented later on. So, first, kind of to note, the surface temperature was kept constant for both of the two samples run with the boiling. Now, we wanted to make sure we were in the nucleate boiling region, so we could use the Rosenthal equation. And as you can see, we're about 10 for our delta TE for either or. So the nucleate boiling would apply. Now, with nuclear boiling applying, for us to calculate the heat properties of the two boiling experiments undergone for soy milk and chocolate milk, we can use the Rosenhow equation, seen here. So there's a lot of properties that go into the Rosenhow equation, and this was arguably the hardest part of the project that I was tasked with, and all of us kind of did together, and making good assumptions and finding good values for these properties. I want to briefly go into this so we kind of are on the same page for what we present and our values later on. So for chocolate milk and soy milk, I'm just going to go through down pretty much the properties. I know it's cut and dry, but I need to get this, articulated. So for the gravitational constant, we're both looking at obviously that of Earth, 9.81. Now for the heat of vaporization, we did find a Cambridge article that uses linear regression to calculate a lot of the values for the Rosenhow, but the correlation factor that they used to find the delta H vape tended to be very similar to that of water every time, so we made the assumption that we can use that of water in this situation as well. Now, for the viscosity, this was a respectively difficult parameter to find based on the fact that there's a lot of different fluids out there, and especially for milks, they're not just like tabulated, like this is the answer. So mainly using a Cambridge University article that published a chart that pretty much varied dynamic viscosity of milk with respect to temperature and fat percent, we were able to obtain, using the fat percents of the properties of chocolate milk and soy milk, the different viscosities. And this graph is shown right here, the 11% and 6% regions being what we cared for in our example. Now, going back, as we went over for the delta TE, the saturation temperature was kind of more so an assumption as we had a little bit of trouble probing, but from our online resources, we were able to see that the boiling temperature of the milks should be a little bit above that of water, but not too substantially above. And we also we made the assumption so that chocolate milk is higher molecular weight and contains a thicker and higher liquid density compound, that it should boil a little bit above that of soy milk. And we use this to factor in for calculating our saturation temperatures. Now for liquid density, just noting, we got this value for chocolate milk from the Food and Agricultural Organization, and the measurement of composition of density, specific heat and viscosity of cow's milk and soy milk for soy milk, which is articles we all have cited in our paper at the end of this presentation as well. Now, for surface tension, this value, again, not one that I can 100% validate that is like this is a tabulated value for this exact milk, but we basically found a Cambridge article that developed a linear regression algorithm to calculate values at different temperatures, and we used this as our assumption for both the chocolate milk and soy milk. And this is from a Cambridge University article that we will have cited later on. Now, for the heat capacities, these values were easier to tabulate as, for example, like the heat of vaporization is not so readily available online because people in the food industry are not really concerned with when milk's going to boil, but they are concerned with when that that freezing point is, and when they get there, how much heat it can hold. So these values were easily found for one, the American Society of Heating, Refrigeration, and Air Conditioning Engineers for the chocolate milk, and the previously cited measurement and campaign of density, heat capacity, and viscosity of cows and soy milk article had these values tabulated. Now, just moving on, the CSF values in the Rosenhow equation, we make the assumption that we can use that property of water, and these were for mechanically polished stainless steel pot. Now, thermal conductivity, another value that was not necessarily completely tabulated, but we were able to get this actually from a slide from Dr. Goldfarb's in the chapter Solutions, and we looked up his values in table 8.9 from a ResearchGate properties table and chart PDF file, and we were able to validate so that the temperature of the CP tends to go down a little bit, so we used a value on the lower side, but that was what we used for our thermal conductivity. And then there is the Prandtl number is directly obtained using viscosity, heat capacity, and thermal conductivity. And all these values are basically put into MATLAB and solve the Rosenhow equation for heat flux, heat capacity, and working backwards to get the effective heat transfer coefficient.
So as Zach was saying, the finding these values was the hardest part of was the hardest and time-consuming part of our experiment. The viscosity values were found by using the nutritional facts on the back of the chocolate milk and the soy milk. We used the percent fats to find the corresponding lines that matched up to the dynamic viscosities we used. Similarly, we found the heat capacities using the 2% of total dissolved solids. Most milks are at 11.6% dissolved solids, so that's the value I used to find the soy milk's heat capacity, which is the last point on that second curve. I assumed that the type of soy milk we were using was the Doko type soy milk. And then that was just the table that we used to find the density of soy milk based on the percent of total dissolved solids. We plugged in the viscosity and the heat capacity to find the Prandtl number. Our Prandtl number is the ratio between momentum diffusivity and thermal diffusivity. And so I took it to mean how much movement transfer was present in a molecule compared to a unit of thermal transfer. And so our soy milk had double the movement transfer for 1 unit of thermal transfer, which makes sense because it has a higher heat capacity, and that's what mostly shaped our Prandtl number being double that of chocolate milk. We plugged in the Prandtl number and all of our constants into the Rosenoff equation to calculate the heat flux, and multiplied that by the area to get the heat rate, and then divided that by the difference between the saturation temperature and a difference between the surface temperature and the saturation temperature to find the coefficient of heat transfer. It wasn't surprising to us that soy milk had higher values for all of those because they plug into each other, and that was mostly because of our heat capacity being double that in soy milk than that of chocolate milk. In terms of the applications of it that Avery was talking about, the heat rate being better for soy milk is going to mean that it's a little easier for soy milk to be introduced as a substitute for vegan options being available in the dining commons or in any dining place where chocolate powder can be mixed in to substitute for chocolate milk. That's it. Thank you. Have a nice day.